right, well, hello everybody. Although I might not be in class today, we can still learn a couple of things and do some practice. So today we're going to be covering the 1.3 section of our textbook, Graphs of Functions. And this video is primarily so that you can learn the different concepts that are presented in this chapter and then go and attempt the practice exercises. So as we go, if there's anything that doesn't make 100% sense, feel free to rewind and listen again, or, there are other people in the class too, maybe they got it. Just respectfully and quietly, you can definitely talk to each other about this. So this first example here, we talked about this last time. We talked about what makes something a function or not a function. So it says, are the following graphs, the graph of a function, why or why not? So last class we talked about this thing called the vertical line test. Let me scroll down just a little bit. So in that vertical line test, if we were to look at a function, let's say this one on the far left, if we're looking at this, remember that we talked about how x can only go to a single y. I can never have one x go to more than one y. So if I picked just any random x point along here, like if I picked right here, and I ask, okay, this x coordinate right here, what's the y value? The y value is this thing right here. Okay, that's fine. As long as there's only one of those, we're good. So like if I picked over here, boom, yep, there's my y value, only a single y value. So this is a function, which we like to emphasize is fun. That was a lame joke. Okay, so let's look at our next one. We have this sideways parabola. Woo! And if we were to do that same test, picking some x coordinate along the way here, let's say you just pick this x coordinate, and I say, hey, what's my y coordinate? Oh, it's that one. Or it's that one. Oh, that's the problem. So because of that, this is not a function. And similarly, our third example over here, this circle, if we were to look at any given x coordinate, we would see, whoop, no good. So that's not a function as well. Now, there is a place on both of these, on the last two examples, where if I were to draw a vertical line, it would only hit at one point. We call that a line that's tangent to this curve. And there are places that happens. That's not what makes it not a function, and that doesn't conflict with it being not a function. It's okay if that happens. It's just, it's not okay if the other thing happens. Our first example here, there's no place where that happens. There's no place where two hits happen. So, if we move on to the next page, you can follow along in the notes packet that I provided for this sub as well. So it says, example 2, find the domain of f of x is equal to the square root of x plus 1. So first we're going to do the algebraic solution to this. And if you remember from last class, domain was x values we are allowed to plug in. And so you might be thinking to yourself, well, let me think about this. The square root of x plus 1, is there a square root that I'm not allowed to take? You might remember from Mr. Marianello's class, we can't take the square root of a negative number. So like if I had the square root of -3, that's bad. And I think you might have talked about it in previous classes. There is an imaginary number that goes with that, but when we're talking about domain, we're talking about real numbers. So we really want to avoid, we don't want negatives. So when we talk about domain, we can say x can be anything as long as the inside doesn't become negative. And there's a way to solve that. We can say, well, the inside, this x plus 1 is supposed to be positive, which we can say it needs to be 0 or more. And so now there's this little mini equation, or sorry, mini inequality that we can solve. So I say x plus 1 is greater than or equal to 0, and I just have to subtract 1 from both sides. And we say x is greater than or equal to negative 1. So as long as we pick a number that's negative 1 or more, we're okay. Let's test that really quick. So if I pick, let me pick a number that doesn't follow that. Let me pick x is equal to negative 2. So if I did that, we would get the square root of negative 2 plus 1, which is the square root of negative 1, which that gives us something imaginary. We're not allowed to do that. But let me pick something within this domain that we talked about. Let's see. So domain that we talked about, we said x needs to be negative 1 or more. Let me just try that bare minimum, negative 1. If I try x is equal to negative 1, when I plug that in, I get the square root of negative 1 plus 1. Ooh, getting kind of close there. Which is the square root of, square root of 0. Can we do that? Oh yeah, 0 times 0 is 0. So we're allowed to do that. And anything bigger, you know, if I plugged in 5, we'd be good. If I plugged in a billion, we'd be good. So that's how we find that algebraically when it's a square root. But graphically, that's a different story altogether. So let's get our graphing calculator out. So here's my graphing calculator. Oh, it's already on. That's good. So I'm going to go to y equals, and clear that stuff out, and go in, and we'll type in the square root of x plus 1. And just to make sure that I'm zoomed where I need to be, I'll zoom standard. I like zooming standard just in case I went somewhere else last time I was graphing. And so we get this. That looks like a graphical bug, that piece at the bottom right. So that shouldn't be there. Regardless, if we look at this, the domain is the x values we're allowed to plug in. So remember, x values are along here. So it looks like the farthest left we get is right around here, and then it just goes. So if we look here, that's the x value, negative 1. So if I was looking at this on a number line, it would be negative 1. I can be there, and then all these. Okay, so that fits the x is greater than or equal to negative 1. So we can always go and look at these things in the graphing calculator. But sometimes I am going to ask you to algebraically do it, to do it without the picture. So just make sure that you're able to do both. Let's clear that out. So if I was taking notes on, I'm going to have to go pull that up later. I just hit minimize and I'm on my second monitor. But if I was going to, take notes on that, I would, kind of like we did over there, I would show the woo like that and go that we started here. We can go forever. So there's another notation for that we'll be looking at in the near future, but this is all we need today. So now if we're talking about range is very similar. Remember, range is the y values that pop out. So going back to our picture, which I'm just going to use this one that I drew because I minimized my calculator and I want to keep this brief. Then if we think about that, the range is the lowest y value to the highest y value. And it may look like this is kind of leveling off as we go, but it does turn out that it does keep on going up and 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 up. So we can say our lowest y value is right here on the x-axis, and it goes up, which I could say y, you need to be 0 or more. Those are the y values that we get. So that's a brief introduction to domain and range. And let's keep going. So the next thing we want to look at is increasing and decreasing functions. So if I want to look at increasing and decreasing functions, a really helpful way is to have the graph. And I've already graphed this one for us here. We can see this curve, the curve of x cubed plus 3x squared. And we want to identify the areas over which, or the intervals over which the function is increasing and decreasing. So, and this is where we're going to use that other notation, that interval notation. So it looks like if we kind of travel, if we trace our pen from left to right, let me get out another tool so we can kind of talk about that. If we trace from left to right, so if I'm going, what was I just tracing as I was going from left to right? Was I tracing going up or was I going down? And since we were going up, we would say that the function's increasing over that interval. And then it stops right here and then starts going down. So we'd say it's increasing, then it's decreasing, and then from here on, it's increasing again. So if we're going to give a rough estimate on these things, we can say that it is increasing from the far left all the way up to, it looks on my picture like it's -2. And then here's 0. So the way that we're going to do this is using something called interval notation. Interval notation goes left, comma, right. So the word least, comma, greatest. So if I have an interval that I'm increasing, well, so if I start all the way over to the far left and then whoop, like that, well, the far left, we call that negative infinity. So I can say this is increasing from negative infinity all the way up to right here, to that x value. I don't care how high it is, I care that it stops. So that x value is -2. And then it does turn out that it's increasing a little bit later, so we'll come back to that in just a minute. And then so from -2 to 0, it looks like it's falling. So we can say it's decreasing from -2 to 0. These are not coordinates. This is a range. This is an interval. So from here to here, wait, you can't see me. From here to here, from here to here. And then we can say that it's increasing again. We don't connect it with a comma, though. We connect with, it looks like a U. It's a symbol that means union. So it looks like we are increasing again from 0 all the way on forever. So we'll say 0 to infinity. So that's how we calculate our increasing and decreasing. And just because of time, we're going to talk more about extrema in next class. So remind me that we need to still talk about extrema. That should be the first thing we do, though. So I want to show you how we find those. There are a couple of different ways that we can do it. We can do it with our calculators, and we can also do it by hand. So it turns out, my visual looking at this right now, I'm actually wrong. Using some algebra and stuff like that, I could find that these numbers, that -2 that I picked, it's not quite right. But if all I gave you was a graph, it'd be absolutely acceptable. So we're going to talk next class about why that's not -2 and why it's actually going to be -3. But don't lose sleep over that. We'll talk about it next time. So here's another one. And again, we're going to have to do our best to estimate off of this graph that we're given, because it's kind of hard to see, but I see an extrema that looks like it's here. And if that's -10 and that's +10, let's see. So we're certainly getting there. We're on our way. So we're not going to be able to exactly say what that is just looking at this graph, and we're going to have to estimate. So I'm going to say this is -2 again, and I'm going to say that's +2 again. And I very well could be wrong, and that's okay, because if all I have is the graph, then that's all I can do. But I can say that it's increasing, again, because I can trace. If I'm going from left to right, I'm going up, 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 up. So I can say it's increasing from -infinity all the way up to that x-coordinate of -2. And then it starts increasing again at this 2 all the way on to infinity. So again, if I just keep tracing off to the right, I'm going to get to infinity. So I say then it starts increasing again at 2 and goes all the way to infinity. And then decreasing. So decreasing, looks like it decreases between those two. So we can say it decreases from -2 up to 2. So you may be worried about what's happening at 2 and -2 because of the bump that happens, which mathematically we call the relative min or relative max or the relative extrema. At that exact point, it's not increasing or decreasing. At that point, it's flat, it's constant. Um, don't worry about that. So that's not like a test question or anything. Okay, so, oh yeah, we're just talking about that. The relative min and max. So if we look at this pink, purple, I don't know my colors. Now it's watermelon. If we look at the watermelon curve, we'll see that boom, right there, we've got a relative min or max. Compared to the points around them, it's higher or lower than all of them. And it's always going to have that kind of bump to it. Sometimes we'll call that a vertex, but like that would be a relative max, that'd be a relative min, relative max, min, max. If you, let's say you flatten out, then keep going, this is nothing. We don't call that a max or a min. So there has to be that change in direction. All right. We have something called a step function. So if we look at this, the cost of postage for a letter, we can see that all the way up to 1, it costs 39. I'm assuming this is in cents. Let's in cents. So 39 cents. And then from 1 to 2 ounces, if you look at 1 ounce, is 1 ounce 39 cents? Or is 1 ounce 41 cents? And that open circle, I'll zoom in here. That open circle that we have says not here. That closed-in circle says it's here. So at one ounce, it's 39 cents. But as soon as we cross over 1 ounce, it jumps up to 41 cents. And so from 1 to 2 ounces, it's 41 cents, 41 cents, 41 cents, 41 cents. We hit 2 ounces, still 41 cents. And then as soon as we cross over 2 ounces, boom. All the way from 2 to 3, it's 43, 43, 43, 43. And then at 3, it's still 43, but as soon, so like if I had a package that weighed 3.02 ounces, that's this, it's OZ is for ounces, 3.02 ounces, that would cost me 45 cents. Or if I had, let's say I had one that cost, or that weighed 5.99 ounces. A Q, that's an interesting way. Let's try that again. 5.99 ounces. So like right here. Well, it's fine. It's still going to be that 47 cents, or I can't read. Let's see. Kind of hard to see. Yeah, I think 47. But whatever that cost is, it's just going to stay there until we get to that 6 point a little bit, and then it's going to bump up in price. So, and this and the other one over here on the left are examples of something called a piecewise function. It's the idea of a bunch of pieces put together. So like here we've got this one line, this line ends here, and then the new line picks up where it left off. So we're going to be learning how to graph those in the near future, and don't worry, it's not as complicated as it might seem. It really is just kind of stitching together different things. So the last piece of our lesson for today is even and odd functions. So I've written it here for you, nice and big. It says even functions are symmetric with respect to the y-axis. Remember, y-axis is this way. So an even function is something where if I were to have, let's say we have a guy smiling. He's got a nose. Now he's not a function, but I think this helps illustrate it. He's not a function because if we drew one of those vertical lines through, we would see, oh, I poked his eye out, my bad, or I guess I sliced his eye out. Poor guy, he's fine, he's fine. But if we were to flip around that y-axis, so in that, what's going to happen is it's going to be a perfect mirror of that. So if we look at our options down at the bottom of the page, we'll see that At the far left, we have this parabola. That's an even function as long as its vertex is on the y-axis. And we'll notice that there's a special thing about even functions where the y values are the same when the x values are opposite each other. So like if this was y is equal to x squared, let's try plugging in 3. So what is y when x is 3? Well, 3 squared is 9, so I get y is equal to 9. What about if I had the opposite x value of that? What if I had y, what would my y be when x is negative 3? Remember, a negative times a negative is a positive, so we get y is equal to 9 again. So 3 or negative 3 gave me the same y value, and it could have been anything. It could have been any x value. I could have picked a billion and negative a billion, or 1.025 and negative 1.025. It doesn't matter. It's going to work. We're going to square that. The negative's going to go away. So then we have an example of an odd function. We go back up here. It says odd functions are symmetric with respect to the origin. So this odd function down here, I guess I can do another smiley face example. So the smiley face example is a lot more challenging to draw with an odd function. So, because not only does the smiley face have to be flipped around the y-axis, it also gets flipped around the x-axis, and it's going to wind up being diagonally symmetric. So, like, it's going to wind up being upside down and reversed. So notice how everything kind of flip-flops here. It flip-flopped that way, and it flip-flopped this way. So like his nose is going the other direction, and the eyes have switched places where they are, and we've turned his smile upside down. But since his whole face is upside down, he's still smiling. It's okay to turn a frown upside down, and it's okay to turn a smile upside down as long as the smile's connected to your whole face, because then you're still smiling. So, and we'll notice with this, if I start with this odd function down here, the x-coordinate and y-coordinate, both of them change sign. So, like, for example, this might be y is equal to, actually, I'm going to use a different example than this, because the function for this is kind of messy. It winds up being a cube root function, so we don't want to talk about that. We're going to talk about y is equal to x cubed. So if I were to pick, let's say, 2, so that's going to be 2, comma, I don't know. Let's find out. So let's plug that in. Y is equal to 2 cubed, which is 2 times 2 times 2, which is 8. Okay. So we have the point 2, comma 8. Now let's examine what happens if I plug in negative 2. So let's see, y is equal to x cubed, negative 2 cubed. So that's negative 2 times negative 2 times negative 2. So remember, a negative times a negative is a positive, so we'll get positive 4, but then we're multiplying by negative 2 again. So we wind up getting negative 8. So we get negative 2, negative 8. And so that's the example of this odd function where we started with 2 positive numbers, then we got 2 negative numbers. So situations that are neither are when, one example is if it's symmetric to the x-axis. Another one is just where there isn't symmetry to either axis or to the origin. So, like for example, if I had something like this. So this is close to the one that we just drew a second ago, but since the middle's kind of here, if I were to flip it around one of the axes, Like if I kind of cut it this way and tried to flip it, well, like, so that would go over here, and that would go. It's not symmetric to the y-axis. We would need something that looked like that. So it doesn't fit either of our categories. So that would be neither. So the way that we test for that, and I showed it just a minute ago, is we try plugging in f of negative x, and we see if it simplifies back to regular old f of x. And then if we were to try f of negative x, and it winds up being the opposite of our original, then we know it's odd. So I will show you what I mean. So we're going to do the test, the even-odd test. So I'm going to do f of negative x, which means plug in negative x. So over here, what that's going to mean is, remember, we're going to rip out x, anywhere we saw x, and we're going to plug in negative x in its place. So let's see what happens here. Let's see. This is a negative times a negative times a negative times a negative, right? So two of them together cancel out and form a positive, so that means it's going to be x to the fourth. Then we'll have that minus sign still in the middle there. And then this says, take the absolute value of negative x. So I can't just say that this is just x. Because, like, what if x was negative 2? The absolute value of negative 2 isn't negative 2. So secretly, what's really happening here is the negative sign is going to disappear. And let's just think about that really quick. What's the absolute value of negative 3 versus the absolute value of negative 3? They're both 3. Ooh, or even versus the absolute value of 3. And so because of that, we don't want to say that it's just x. We want to say, we want to keep those absolute value bars, but we can ditch the negative because it's not going to matter. We could put as many negatives, negative, 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 however many you wanted to throw on there, it's still just 3. So because of that, if we look at this closely, we'll see this and this are identical. That test shows us that this is an even function. If we look at our second one, it's x over x squared plus 1, and it's g this time. So let's try g of negative x. So that's a negative x on top. It's a negative x squared plus 1. So let's see what happens there. We have a negative x on top, a positive x squared down here. And so far, that's looking kind of weird. Can I get it to say negative g of x? Well, if I were to divide both sides by negative 1, we would see that we have x over x squared plus 1 is equal to negative g of negative x. And if we go back and we look at our tests, we can see that if f is odd for each x in the domain of f, then f of negative x is equal to negative f of x. So we were able to get that double negative to show up, which shows us that this is an odd function. So another way for us to look at this is actually probably a lot simpler for most of us in here. We could have just simply said, well, there's a negative 1 times that, which that is the definition of what the opposite is. The opposite is if you multiply by negative 1, then we're good. So that might have been a little bit simpler. Sorry for the more complicated explanation first. Then if we look at number 3, h of x is equal to x plus 6. If I try that this time, h of negative x, let's see what we get here. We get negative x plus 6. So Is that equal to h of x? No. Is that equal to the exact opposite, which in this case would be negative x and a negative 6? No. Because of that, this is neither, or neither, or nether. No, it has an I in there. It needs to be one of those. So it's neither, and that's everything we need for our assignment. So again, if you need to rewatch part of this video, go for it, and we'll talk about this next time in class. Oh, now I'm walking across the room because I minimized the recording. And let's see, where is the recording? And